Hello and welcome everybody. Today in calculus we will be talking about optimization. So basically taking everything that you have learned about how to graph a function, finding the absolute maximum, absolute minimum, and applying it to a word problem. So basically just the idea right here. Given that you have a scenario with boundaries and restrictions, I want to obtain the absolute maximum or absolute minimum. That's what optimization means. So here, let's just go ahead and jump into an example so you can see what I'm talking about. So in the picture on the right, you can see that we have an ellipse, and here's what I want to do. I want to find out what is the dimension that will yield the largest rectangular area that can be inscribed in the ellipse at x squared plus 4y squared is equal to 16. So what's happening is you have your curve, which is going to be that equation that I gave you. And inside, I want to draw a rectangle, and I want to optimize, or I want to find the point, the coordinate, x comma y, where it touches the ellipse, and I want to find out what is the maximum largest possible area of that rectangle that I can obviously get. So let's go ahead and dive into it. So first off, what we're going to do is we're going to go ahead and define what is the area in terms of what we have. Now, since my coordinate where it touches the x-axis, not the x-axis, but where it touches the curve is going to be some arbitrary point x comma y, then we say the area is going to be 2x times 2y. The reason why it's 2x and 2y is x is only located from here to here. And that means that you have another part right here, so that's why it's equal to 2x. And similarly, vertically, y only goes from the y-axis all the way to the top. And then since you have to go down also by that amount, then that means there's a total of 2y. So you don't have to worry about positive and negative, assuming that we're keeping x and y to be positive then. All right, so that's where the 2x and the 2y came from. And I'm going to go ahead and clean up that equation. And that's where we got the 4xy. Now, thinking about how we've been doing things so far, since I'm trying to find the maximum area, then that means it's most likely I need to take the derivative of this equation and then set it equal to 0 or undefined. But what I don't like about this equation is that there are two variables because it's x and y. So what that means is I need to make a substitution. And that's where the equation of the ellipse actually comes in. This x squared plus 4y squared is equal to 16. So on the side over here, you can see that I did a solving for x over here. So x squared plus 4y squared is equal to 16. I isolated the x squared, and then afterward isolated the x. So then that way I can take all this guy and throw it into here, replacing x with that nasty looking square root thing. So now my function of the area is strictly with respect to y, and that's good because now I can actually take the derivative. Can you solve for it so that it's an area of function of x? The answer is yes. You do whatever is convenient for you or whatever if you feel like at that point. So nonetheless, now I'm going to go ahead and take the derivative, which is right below. So just to kind of spare you the gritty detail right here, I am taking it using the product rule and also using the chain rule. So that's where the nasty thing comes up. And remember, we're going to go ahead and take this guy and set it equal to 0. So ideally, what I need to do now is clean this up as much as possible. So get it under a common denominator, and then also rationalize it as much as you can, and also keep it in factored form. All of that stuff that you were told to do or asked to do when you first solved for the derivative. And this is where it comes into fruition. So in the very end, if you did everything correctly, right, you can follow my math or you can stop the video and look at what happened. Basically, what you end up with is this equation that's down here, which I kind of erased a little bit, but hopefully not too much. You end up with this thing, 16 times 2 times y squared divided by 4 minus y squared all in the square root. And since I'm looking for, once again, the critical point, I am going to set the numerator equal to 0. And also set the denominator equal to 0 because we're looking for when the derivative is equal to undefined or equal to 0. So you can see now the next part, I solve for each one of those y values. And in the top part, we get y is equal to plus or minus root 2. Whereas the bottom part, we get y is equal to, technically, it should say plus or minus 2 as well. But remember, in our problem, since x and y represents part of the length and part of the width, what we're going to do is we're going to go ahead and reject the negative answers just to make things a little bit simple because it doesn't make sense for area to be negative. So for each one of these, I'm just going to go ahead and look at the positive part and also over here, just the positive part. So one is root 2, the other one is going to be 2. Now, the problem with 2, though, is that 2, if you notice for y, it is actually the lowest possible point or the highest possible point. So what that means is, yeah, you will actually optimize it, but the optimization in this case, the area would get you 0, because if y is equal to 2, there is no room for x to be anything else but 0. So what that means is, even though that's an answer, it's most likely we're gonna go ahead and reject that one, because this is going to be an endpoint. Okay, endpoint where a is equal to 0. All right, so my focus then is going to be this critical point over here, which is root 2. Now, again, thinking back to what we did with the graphing, what we're now going to do is we're going to create a chart, a sign chart, to see what's happening with the derivative and then correspond that to what's happening in the original function. So what I did was I took values of x that is going to be less than root 2 and greater than 0. And then I am going to go ahead and plug it into my derivative equation, which is over here. So for example, in this interval right here, I'm going to go ahead and let's say x is equal to 1. Oh, sorry, not x equals to 1. Y is equal to 1. So I'm going to throw y is equal to 1 into my derivative equation, and it comes out to be positive. So because it's positive, then that means that my original function, a, is going to be increasing, because positive derivative means that it's an increasing function. Whereas if I take a value that is greater than root 2, but less than 2, right, and I plug it into the derivative, maybe like say 1.7, and in this case, you might have to use a calculator, you're going to find that you're going to get a negative value, and that's where this negative is coming from. So because the derivative is negative, then that means that your function is going to be decreasing. Judging by the curve, how is it increasing and decreasing in A, that tells me that you are going to hit a local maximum in this case, because you're increasing and then you're going to be decreasing. So what we want to say, and this part is actually crucial, you actually have to say it, because a prime changes from positive to negative at x equals to root 2, then by the first derivative test, because that's what we're using right here, there is a local maximum at x equals to root 2. That's how you justify your answer. Okay, so make sure you actually do that then. If you just give a chart, they won't give you credit for it, and in fact, you probably just will lose the points in that case. Okay. All right, so that is going to be my first derivative test. And by the way, if you're looking for a local minimum, then you would expect that you would go change the sign from negative to positive then. Okay. All right, but anyhow, at this point, now that we know that y is equal to root 2 is going to be my local maximum, we're going to now plug it back into the original equation. But at the same time, remember, your local maximum and your local minimum is not good enough. I'm looking for absolute maximum and absolute minimum. So what that means is we're going to have to check the endpoints then of the interval as well. And by the endpoints, remember, that's when y is equal to negative 2 and also equal to positive 2. Actually, we don't care about negative 2 because, again, y is going to be a positive value because it's height. All right, so here I wrote down a of y, the function. I'm going to go ahead and plug in one endpoint, which is 0, right? Because that's the smallest possible value of y that we can put, which comes out to be 0, which makes sense because that's just a horizontal line. If you go back to your graph right there, when y is equal to 0, you don't even have an area because x would then have to equal to 4. Then I'm going to go ahead and plug in a of 2, meaning when y is equal to 2. Well, that is now going to be a vertical line, and there's no value of x, as we said earlier, so that's also going to give you 0. And finally, we're going to go ahead and put in the root 2 that we got for an answer. And look at that. It comes out to be an area which is equal to 16. Well, looking at all the values that we have, we can conclude then in this case that this right here, even though we solved for it as a local minimum, local maximum, it turns out that this is also going to be an absolute maximum because that is going to be the largest possible area that we can get out of this. Well, now, if necessary, we can find out what is the coordinate of that point. We know the y value, which is going to be equal to root 2. So here you can see I'm going to solve for the x value then, if they ask for it. So plugging y back into the equation of the ellipse, we're going to get x is then equal to 2 root 2. So if the problem asks for it, go ahead and solve for it. But if it doesn't, if it just asks for what is the largest area, then you're done. Okay, so here you can see in the box, I actually drew that picture because the length is supposed to be equal to 2x. That's where I got the 4 root 2. And then the height is supposed to be equal to 2y, and that's where I got the 2 root 2. And if you multiply those together, you definitely then get the 16. All right? So there is a procedure to all of this stuff that we're doing because, it sounds like there's a lot of work, but there is a strategy behind it. And let's go ahead and talk about that. So then that way you can prepare the strategy every single time. And I scrolled back up just so that all my lines over here can actually appear once again. So here we go. Let's go ahead and talk about the strategy for each of these prompts. First one, what you're going to do is we're going to come up with an equation that you want to maximize or minimize. That's easy enough, right? We want to find an optimization, so we need an equation to take the derivative of. That's what this is for. Now, if this equation above that we just found contains more than one variable, which happened in this case because there was an x and a y, then what you need to do is you need to find another equation to relate those variables and then make a substitution of your second equation into the first. So then that way, your equation that you have that you want to optimize is strictly just f of x or f of y. So that's exactly what I did over here. Notice that once again, what I did was my function for the area is in terms of x and y. And then now afterwards, I took the equation that related x and y and made a substitution so that I have a function strictly of y then in this case. And again, you can solve for it in terms of strictly of x if you want also as well. All right, now that we have that equation, then step 2 is going to be differentiate the equation. So take your equation and take the derivative of it and find its critical point by setting f prime equal to 0 or undefined. So that's where we had to kind of clean it up a little bit. And then afterwards, set the numerator and the denominator equal to 0. And then here, now this is the part where it's crucial once again. You need to draw a sign chart and conclude with the first derivative test, which is what I did. Or there's another option if you want. Solve for the second derivative at x equals to a, where a is supposed to be that critical value. And then you're going to conclude with the second derivative test. Now, for those of you guys that don't remember the second derivative test, we're going to go ahead and look at an example of one where you actually get to use the second derivative test instead. You can use either one of those tests, but just make sure you actually use those tests then. Finally, once you conclude that the critical value is either a local maximum or local minimum, then the last thing we're going to do is we're going to plug in your critical values and the endpoints into your equation to figure out if it's an absolute maximum or absolute minimum or neither then. Okay? All right, so those are going to be my strategies, step 1, step 2, and step 3. Sounds so easy so far, but there's actually a lot of work in between, so you just got to be very careful, all right? So here it is. Here's the second example where we're going to use the second derivative test instead of the first derivative test. And again, the option is up to you, whichever one you want to use, because, one might be easier than the other. It's up to you. All right, here we go. An open box with a depth of x can be created by forming a rectangular sheet of cardboard by cutting squares of sides x from its corner. What is the largest volume such box given cardboard that measures a 20 by 30 inches? So here is what I'm trying to say. Here is a picture on the right hand side of that cardboard that is 20 by 30. What I'm going to do is I am going to cut out each corner by a certain amount, and each corner will be cut out is going to create a small little box right there. So we don't know what's the size of it, so we'll just go ahead and call it X. And once we do so, we can kind of fold along the perforated line that I'm drawing right now. And if you do so, then you're going to be able to create an open top box. And I'm pretty sure most of you guys have done this when you were younger, when you're trying to do some sort of like art craft or whatever it is. Nonetheless, here is the picture of what it looks like. I want to know what is the largest volume that you can get out of this. Okay, I want to know what is the largest volume that you can get out of this. So first of all, let's go ahead and create some variables, and then afterwards, we're going to go ahead and solve for this then. Let's go ahead and denote the length that you're going to cut out for each square will be x. And in this case, we're kind of lucky because we don't have any other variables that we're going to be dealing with. Now you're going to fold the box. So then that means the bottom part is going to be 30 minus, I got to be careful here, 30 minus 2x, right? Because you can see the 30 is going to be the length, but there's an x that's over here and an x over here. So this length right here, that is why it's 30 minus 2x. Then for the width over here, that should then be similarly 20 minus 2x because there are x over here and then also an x over here. And finally, folding upward, the height will be just equal to x. So putting it all together, the volume of that box is supposedly normally be length times width times height. And I took the length, the width, and the height and translated it so that it's all in terms of x, which is nice because now we have a single variable that I can take the derivative of. So we're going to clean up that equation. V of x is equal to this guy, and that's going to be my step 1. Step 2, now if you remember, is to take the derivative of this equation and set it equal to 0 or undefined. So that's an easy enough task because it's a polynomial, and I'm going to go ahead and set it equal to 0. Now at this point, you can use the quadratic formula to solve for it, or you can just ask your calculator to use the 0 option to solve for it. So that's what I did over here, using the 0 option on my graphing calculator, and yes, that is viable, so then that way you don't have to actually show your work. All they care about is actually your answer at this point, so you don't have to like tell them what you did from here, you just have to actually just write that you used the 0 on your graphing calculator and give them the answer, and that's it. You don't have to show the work that is involved. So we get 2 answers in this case. We get x that is equal to 12.743, or x is equal to 3.924. And just like the previous problem, it sometimes comes out to be the case where one of these actually doesn't make sense because it's out of the boundary. Even though we were able to solve for it, it's unfortunately an extraneous solution. Well, if you want to know which one is the extraneous solution, let's go back up to the top over here where we said that the length is supposed to be 30 and the width is supposed to be 20. Now, since you have x's on both ends, that's where we got the 30 minus 2x, and that's where we got the 20 minus 2x. Imagine what would happen if you plug in one of these values of x, like say, for example, 12.743 into maybe like say this guy. That will come out to be negative, and that's where it doesn't make sense. So what I'm saying is this guy right here, that is going to be an extraneous solution, but because when you plug it in, your volume is going to be equal to something that's negative, and that's not what we want because it's irrelevant. So the only one that we care about is going to be this guy right here, which is 3.924. And remember, always round it off to 3 decimal places. Once we have our critical value, right, we now go ahead and do the following then. Well, since I promised you that we're not going to use the first derivative test by using a sign chart, I'm going to show you how the second derivative test works, if you remember how it works. So the second derivative test, needless to say, what we need to do first is solve for the second derivative, which is located right here. So by using the power rule one more time, that's what I get. Now I'm going to go ahead and plug in my critical value into the second derivative, and it comes out to be negative in this case. So you can see that value right there. Now, thinking about how to translate all of this, okay, remember, this is a critical value. So that means that it is going to be a local maximum or local minimum. The slope is equal to 0 at that point. The second derivative talks about the concavity. If your second derivative is negative, then that means it's concave down. Well, drawing the 2 scenarios so you can see how it works, right? Here you have your local minimum. And this graph, the only ways for you to get a local minimum all around it, you can see everywhere is going to be concave down. But whereas if we have a local maximum, right, the curve over here is going to be, oops, sorry, I drew it wrong. I didn't even draw that one correctly. I accidentally had it mixed up, so my fault. Give me 1 second to kind of back up a little bit. The top example was where we have a local minimum. And then you notice that in this case, it's going to be concave up, actually. So that means the first derivative, a second derivative, should then be equal to a positive number. But whereas for the bottom equation, or the bottom curve, you see a local maximum. And because of concavity, you can see that f double prime is going to be less than 0 because it is concave down. So the conclusion according to the second derivative test, here's what we can say then. By the second derivative test, and you don't have to write the part that's in quotation right here, since v prime of 3.924 is equal to 0, verifying the critical point, and plugging the critical point into the second derivative and getting less than 0, meaning that it's now concave down, then by the second derivative test, you actually have a local maximum there. Okay, so that's how the second derivative tests work. So if you plug it into the second derivative and get something that's positive, then that verifies that it is a local minimum then in this case. right? So it all depends. If the second derivative is easier to solve for, use the second derivative test. But if it's easier to just draw the sign chart, then go with the first derivative test. Okay. Finally, step 3, we're going to go ahead and plug in the endpoints and also the critical values to see which one's which. So you can see I kind of did that ahead right here. So you're going to plug in 0. You're going to plug in 15 because 30 divided by 2 is equal to 15. That's where I got that from. And finally, we're going to plug in 3.924. And you can see now that that is going to be an actual volume with a numerical value, and that has to be my local maximum, according to what we said, which is also my absolute maximum, because if you check the endpoints, there's nothing that's bigger than that.